So now for determining sample size. There are going to be instances where we want to collect sample data in order to estimate a population proportion for a certain confidence interval. And so let's say, for example, that we want to collect enough data to get a confidence interval with 95% confidence level. Our first question here when conducting this study is, what is the minimum sample size needed? Now this is useful for two reasons. Well, one, obviously, because we need to collect this number of samples. And the second is that if it would be unreasonable to collect this number of samples, then perhaps we can do two things. We can either expand our confidence interval, or we can maybe pick a different attribute or a different population or subgroup. And so we can use this formula. And this formula for minimum sample size uses this confidence level to find this critical value that we talked about. This critical value where p hat and q hat are the proportion of successes and q hat is the proportion of failures. And then E is this margin of error, and that's going to be squared. So there are no new variables here, we're just using them in a different way. And if you look back at, let's look back at this other equation for error. If we look at this, right here, this equation for margin of error, can't we see that we just reworked this n? So we're just solving n from this equation for margin of error. So it's really nothing different here. We're just solving for a different attribute. Okay. And so we have a couple rules here. Number one, if p and q are not known, we're just going to replace each by 1/2. That's our best guess of successes and failures. Finally, we're going to round n up to the next integer. Very important here because we know that n is a minimum sample size. And so if, for example, I find that I need 482.1 samples for a certain confidence level to create that confidence interval, then in reality I need 482 samples. So just making sure we know that n is just the minimum number of samples. We can't take any kind of fraction of a number of samples. And so let's go ahead and do an example of this. An investor is considering funding of a new video game. She wants to know the worldwide percentage of people who play video games, so a survey is being planned. How many people must be surveyed in order to be 90% confident that the estimated percentage is within 3 percentage points of the true population percentage? We've got a few things here. Now we know that this formula, let's just start out there, is that n is equal to the critical value, squared, times p hat, the successes, q hat, the failures, divided by the margin of error squared. All right. Now let's start off with this critical value here. We can find this critical value. We're 90% confidence. This is a pretty standard confidence level, so let's just see if it's on our chart under the positive z-scores, and we've got 90% confidence level. Great. Critical value is 1.645. Okay, we need our p hat, our proportion of successes. Now, this isn't in the problem, and we're to assume that nothing is known about the worldwide percentage of people who play video games. And so our p hat is going to be 0.5. Likewise, our q hat is also going to be 0.5. If we don't know this percentage, we're going to go with 1/2. And now for the margin of error. The wording is a little bit strange, but it says that we want to be 90% confident that the estimated percentage is within 3 percentage points of the true population percentage. All that means is that our margin of error is 3%, which we're always going to convert to a decimal, and so E is just 0.03. And so that's our error. And so now we can calculate this n for the given values. And we get that this is the quantity 1.645 squared times p, which is 1/2, times q, which is 1/2, divided by e squared, so 0.03 squared. And let's throw this in our calculator, and we get 751.67. And so because I know that this is a number n, I'll just add this for our notes. This is equal to 751.7, which rounds up to 752, remembering that n is always the next whole number. And so now what if 16% of people play video games? Well, then the only thing that changes is our p hat and our q hat. Now everything else is the same, but our p hat is 0.16 and our q hat is just 1 minus 0.16, which is 0.84. And so our n is going to be the same thing, 1.645 squared times 0.16 times 0.84 divided by 0.03 squared. So I'm going to do the same thing in our calculators, except I'm just going to change this value of 0.25. So let me just go about it this way. Pressing second answer will just give me the same thing I started with, and I'm going to replace this with 0.16 times 0.84. Okay. And I get 404.099, and I know that 404.1 is going to round up to 405. And so this is our new n if we know the number of people that play video games. And so here's our question. We know that this number decreased significantly once we knew the percentage. So does the knowledge of sample size of successes and failures always decrease the minimum sample size? And so that's just something to think about. Think about it this way. What is the largest value of p hat times q hat if both of these need to add up to be equal to 1? And you calculus folks might be thinking about this in terms of some optimization problem, right? If p hat times q hat needs to be maximized. Well, if we did do this maximization problem, which we're not going to because not everybody in here has been through Calculus 1, I believe, we would know that the value that would maximize p hat q hat when p hat plus q hat is equal to 1 is 1/2, is where p hat is equal to q hat, which is equal to 1/2 or 0.5. And so does the knowledge of sample proportion always decrease the sample size? Yes. Unless the proportion of successes and failures is 1/2. So unless p hat equals 1/2. If p hat equals 1/2, we know q hat equals 1/2. All right, so that's just kind of something to think about, a pattern that you'll see.